All right, welcome back to the deep dive. We're tackling a really innovative paper today, Vision as LoRA, or VoRA, the core idea, and this is the super quick takeaway for the short form edit. VoRA turns large language models into multimodal LLMs without needing external vision modules.
That's the key bit, yeah.
It does this by integrating vision-specific LoRA layers directly into the LLM. And the cool part is, these can be merged after training for practically zero extra cost at inference. Plus, it handles like any image resolution.
Which is a big deal.
Definitely. They use a clever blockwise distillation from a pre-trained VIT to really boost the visual understanding and bi-directional attention masks for images so it can see the whole picture. Even with just additional pre-training data, VoRA performs right up there with traditional encoder-based MLLMs.
Pretty impressive results.
So today, we're diving deep into the Vision as LoRA paper to really understand how this efficient MLLM architecture works. If you're keeping up with the latest in AI research, especially in, multimodal models, this is one you won't want to miss as we unpack their key architectural innovations and findings.
Absolutely. It's a fascinating approach.
Now, to set the stage, let's think about the usual suspects in the MLLM world. You've typically got a pre-trained vision model, think vision transformer or VIT, then some kind of connector to bridge the gap, and finally your large language model. Figure 1A in the paper gives you a clear picture of this setup.
The classic modular design.
Exactly. But as the authors rightly point out, this modular approach has some inherent drawbacks. We're talking about the added computational expense of running that whole vision encoder. And then there's the common limitation of fixed input resolution that many VITs are trained on, which isn't always ideal for real-world varied images.
That's precisely right. You can often find yourself constrained by specific image sizes or, having to implement workarounds like tiling, which can introduce its own complexity.
Yeah, and extra processing.
And fundamentally, the LLM has to wait for the entire vision encoding and connection process to finish before it can even begin its work. It adds latency.
Okay, so that perfectly sets the scene for VoRA. The central innovation here, as you can see in Figure 1B, is to directly embed vision understanding within the LLM itself using those low-ring adaptation or, LoRA layers.
Right.
The truly ingenious part is that this completely eliminates the necessity for a separate external vision encoder during inference.
Exactly. It's all about, internalizing that visual processing, the visual processing capability within the LLM's architecture. So let's get into the nuts and bolts of how they actually implement this vision as LoRA concept while maintaining stable training.
Right. Vision as LoRA for stable training. Let's unpack that. The paper details how they integrate these LoRA layers directly into the LLM to give it visual intelligence. During the pre-training phase, illustrated in Figure 2A, the images are first converted into vision embeddings using a relatively lightweight MLP, just around 6 million parameters.
Which is pretty small in the grand scheme of things.
Tiny. And this includes positional encodings to keep track of where different parts of the image are.
And these LoRA layers aren't just applied haphazardly. Crucially, they're specifically applied to the linear layers within the first NVIT blocks of the LLM. Now here, NVIT refers to the number of transformer blocks in the LLM that are aligned with the teacher VT's architecture.
Ah, okay.
This deliberate matching is key for the knowledge transfer process we'll discuss later.
Absolutely. And this is a really critical point for training stability. Only the parameters within these newly introduced LoRA layers and that initial vision embedding layer are actually trained. The original massive parameters of the pre-trained LLM are kept completely frozen. It's like giving the LLM targeted visual training without disturbing its foundational language knowledge.
This decoupling of parameters is absolutely fundamental. By not attempting to retrain the entire LLM on this entirely new visual modality all at once, they effectively sidestep those significant issues of unstable training and even, catastrophic forgetting of the LLM's original language abilities.
Which is a huge problem.
Which, as we've seen in earlier attempts at encoder-free MLLMs, can be a major hurdle.
Right. It's like giving the LLM visual training wheels that you can later remove without it forgetting how to ride the language bike. Then, when it's time to actually deploy the model, the inference phase, shown in Figure 2B, those specifically trained LoRA layers can be seamlessly merged directly into the base LLM's weights.
And this merging is where that near zero overhead at inference comes from. Because those LoRA parameters effectively become part of the LLM's weight matrices, you're not adding any extra layers or modules that need to be computed separately during inference.
So it's just the base LLM again, but now with vision baked in.
Exactly. It's a truly elegant way to incorporate visual capability without the runtime baggage of a separate encoder.
Okay, so they've established the vision as LoRA framework for stable training, but the next logical question is, how do they actually get those LoRA layers to learn meaningful visual representations quickly and efficiently? That's where the Blockwise Distillation strategy comes into play, right?
So I see. To really accelerate the learning process and mitigate the need for truly vast amounts of purely visual training data, they employ a blockwise distillation strategy. The fundamental idea here is to transfer the rich visual knowledge that's already encoded within a pre-trained VIT into those newly integrated LoRA layers within the LLM.
So instead of just training from scratch on raw images, they're essentially getting expert guidance from a teacher model that already possesses a strong understanding of visual features. How does this blockwise aspect of the distillation work?
Well, the crucial point is that they're not just looking at the final output representation from the VIT. Instead, the intermediate visual representations produced by each transformer block within the first NVIT layers of the LLM, which are the ones augmented with the LoRA layers, are explicitly forced to align with the corresponding block-level feature representations coming from the teacher VIT.
So it's a layer-by-layer transfer of knowledge, not just a transfer of the final result. The paper mentioned the distillation loss in equation 1. Can you break down the intuition behind that?
Absolutely. For each block indexed by I and each visual token positions as, the distillation loss aims to maximize the cosine similarity between the projected LLM features and the VIT embeddings. Now think of cosine similarity as a measure of how aligned two vectors are in direction, irrespective of their magnitude.
Got it.
They use what they call an aux head, which is essentially an RMS norm layer for stabilization, followed by a linear projection layer, to ensure that the LLM's internal representations are in a comparable format to the VT's embeddings. The loss penalizes the model when these projected features are not closely aligned in direction. Does that make sense?
Yeah, that makes perfect sense. Aligning the directions. And then equation 2 essentially aggregates this across all those relevant blocks.
That's right. The overall distillation loss, LDISIL, is simply the average of these per block distillation losses calculated across all of the first NVIT blocks. This ensures that the LLM learns to produce VIT-like representations at multiple levels of abstraction, capturing both low-level and high-level visual features.
Interesting.
By aligning these intermediate representations, the LLM learns a more hierarchical understanding of visual features, mirroring how the VIT processes information from low-level details to high-level concepts.
Okay, so that clarifies the distillation aspect. And it's important to reiterate that during this entire distillation process, only those newly introduced vision-specific LoRA layers are being updated. The core parameters of the original LLM remain untouched.
Precisely. It's a very targeted learning process focused on injecting visual understanding into those specific, adaptable LoRA parameters. They also have equation 3, which represents the standard cross-entropy loss for language modeling, calculated on any image caption pairs they might be using in conjunction with the distillation.
Right, standard stuff there. And then equation 4 neatly combines these two objectives, the distillation loss and the language modeling loss, into the final training objective that guides the entire learning process.
Exactly. It's a multi-objective optimization that encourages the model to learn robust visual representations through the distillation signal, while simultaneously maintaining its ability to generate coherent and relevant text based on the image captions.
Now, one of the more fascinating architectural choices they discuss is the use of bi-directional attention masks specifically for processing images. Most large language models rely on causal masks for text generation, right? What's the fundamental difference here, and why is bi-directional attention more beneficial for images in this context?
You've highlighted a really key architectural decision here. Standard LLMs, designed for generating text sequentially, utilize causal attention masks, as illustrated in Figure 3a. This type of mask restricts the model's attention such that when processing a particular word in the sequence, it can only attend to the words that have appeared before it.
Right, looking backwards only.
It's a unidirectional flow of information, essential for autoregressive text generation.
That makes perfect sense for generating text one word at a time. But images aren't inherently sequential in the same way that text is, are they?
Not at all. With an image, all the different patches or tokens that represent the visual information are present simultaneously. There's no inherent order. Therefore, for effectively processing images, VoRA cleverly swaps out that standard causal mask with a bidirectional attention mask, which is shown in Figure 3b.
Oh, okay.
This bidirectional mask allows each individual image patch to attend to all other image patches within the same input image.
So it's like giving the model full visibility across the entire visual input, enabling a much richer understanding of the global context and the intricate relationships between different visual elements within the image.
Precisely. It empowers the model to capture far more comprehensive contextual information within the visual domain itself. Now, importantly, they retain the standard causal masking mechanism for the text portions of the input.
Ah, that's key.
This ensures that the LLM continues to process and generate text in the conventional autoregressive manner, which is crucial for its language generation capabilities.
That makes perfect sense, employing different attention mechanisms tailored to the specific characteristics of each modality. The paper does present some compelling experimental findings in Section 5 that really underscore the positive impact of this bidirectional attention on VoRA's overall performance.
Yes, their ablation studies provide clear evidence that using bidirectional attention for the visual tokens consistently leads to both a reduction in training loss and a significant improvement in performance across a range of downstream multimodal benchmark tasks compared to the baseline of using causal masking uniformly across both modalities.
Really validates that choice. Now, let's shift our focus to the data that fuels this learning process. What kind of data sets did they utilize for the crucial pre-training phase? Table 1 in the paper gives us a detailed overview.
They primarily leveraged two key image caption datasets, Datacom 29M Recap and GLDV2 Recap. The Datacom 29M Recap dataset is particularly noteworthy. The authors actually generated captions for a carefully selected subset of approximately 29 million images from the massive Datacom 1B dataset.
Wow, 29 million.
Yeah, they used the powerful Qwen2 VL72B model for this captioning process, specifically focusing on images with a longer edge dimension exceeding 448 pixels.
So they essentially curated their own large-scale captioned image dataset tailored to their specific requirements. What about the GLDV2 recap dataset? What role did that play?
They incorporated around 1.4 million images from the Google Landmarks dataset V2. The primary rationale behind including this dataset, as the authors explicitly state, was to address a potential limitation they identified in the Datacom 29M recap dataset, a relative lack of specific world knowledge, particularly concerning recognizable landmarks.
Okay, filling a knowledge gap. That makes logical sense. A more general, broad dataset like Datacom might not have the depth of information on very specific categories like landmarks.
Exactly.
And it appears they also integrated a diverse mix of text-based instruction data into their pre-training regimen. What was the key motivation behind that?
Even though VoRA cleverly decouples the vision and language parameters during training, the researchers observed that prolonged training solely on image caption data could lead to a slight degradation in the LLM's ability to effectively follow complex instructions.
Interesting side effect.
Yeah. Therefore, to counteract this potential issue and preserve the pre-trained LLM's strong instruction-following capabilities, they carefully mixed in a variety of text-based instruction datasets, including Infinity Instruct 3M, Smalltalk, OpenOrca, and several other relevant datasets meticulously listed in Table 1.
It really highlights the delicate balancing act in developing these multimodal models, doesn't it? You need to imbue them with new sensory understanding without compromising their existing core strength.
Absolutely. It's a constant trade-off.
Now let's delve into the results that validate their approach. Section 5 of the paper provides the details of their experimental setup and those all-important ablation studies that shed light on the impact of their design choices.
Absolutely. For their primary training configuration, they employ the AIMV2 huge 448p vision transformer as the teacher model for the distillation process, and the Qwen 2.57b instruct large language model as their base LLM. They maintained a consistent learning rate of 0.0002 and utilized a global batch size of 256 for their training runs.
Pretty standard setup for this skill. And then they conducted a series of ablation studies, which, as you said, are crucial for dissecting the contribution of each key component of their proposed VoRA architecture. They systematically investigated the impact of factors such as the rank of the LoRA layers, the type of attention mask employed for visual processing, and the specific distillation strategy used.
Right.
Figure 5 visually presents the pre-training loss curves under these different experimental settings, and Table 2 provides a quantitative snapshot of the resulting performance on a range of relevant benchmark datasets.
One of the initial and quite significant findings, which Figure 4 visually confirms, was the inherent instability encountered when attempting to directly train the full LLM with the new visual data without the stabilizing effect of the LoRA layers.
Ah, the loss spike.
This direct training approach led to a pronounced spike in the loss, a phenomenon they aptly term loss collapse, which echoes similar observations in earlier research exploring encoder-free multimodal learning.
So the incorporation of the LoRA mechanism really does appear to be essential for maintaining a stable and effective training process when introducing this new visual modality directly into the LLM. What did they observe when they experimented with varying the rank of these LoRA layers?
Figure 5 demonstrates that employing a LoRA rank of 1024 resulted in a slightly lower overall pre-training loss compared to using a rank of 512. This trend was also reflected in the distillation loss, as we can see in Figure 6.
Okay.
While both of these configurations ultimately achieved a comparable average benchmark score as reported in Table 2, the consistently lower loss values suggested that the higher rank of 1024 offered a better optimization landscape. However, they also discovered that pushing the LoRA rank too high, specifically to 1536, led to increased training instability.
Oh, interesting.
Indicating that there's a sweet spot to be found. Consequently, they settled on a LoRA rank of 1024 as their default configuration.
It's that familiar story in deep learning, isn't it? Finding that optimal balance where the model has sufficient capacity to learn the complexities of the task without becoming overly parameterized and prone to instability.
Exactly. More isn't always better.
And we've already touched on the importance of the attention masks, but their ablation studies really underscored the significant benefits of using bidirectional attention specifically for the visual input.
Indeed. Figure 5 clearly illustrates that across various combinations of LoRA rank and distillation strategy, the use of the bidirectional attention mask consistently yielded a lower training loss compared to the scenario where a causal mask was applied uniformly across both the visual and textual inputs.
Clear advantage there.
This observation was further corroborated by the lower average distillation loss seen in Figure 6. Quantitatively, as Table 2 highlights, the switch to bidirectional attention for the visual tokens resulted in noticeable and consistent performance gains across the evaluated benchmark datasets.
And then there's the comparison between the blockwise distillation approach versus just applying distillation to the final transformer block of the VI. Figure 6, which shows the average distillation loss across the blocks, strongly suggests that the blockwise strategy is more effective in transferring knowledge.
Yes, applying distillation solely to the output of the final transformer block did provide a noticeable boost in training efficiency, as evidenced in Figure 5 and the corresponding performance metrics in Table 2. However, extending that distillation process to encompass all of the first invit blocks, the blockwise approach led to a further enhancement in overall performance.
Even better results.
Resulting in even lower training loss and improved scores on the benchmarks. Figure 6 visually confirms that the blockwise strategy leads to a lower average distillation loss across all those intermediate blocks, indicating a more comprehensive and effective transfer of visual knowledge from the teacher VIT.
They also conducted an interesting analysis of data efficiency, which is always a crucial consideration in machine learning research. Figure 7 illustrates how many training steps were required to reach specific loss thresholds under different configurations compared to a baseline model.
That particular analysis is quite revealing. It clearly demonstrates that combining the use of bidirectional attention with the blockwise distillation strategy significantly improves the data efficiency of the VoRA training process.
So less data needed, potentially.
Potentially, or faster training to the same point.
Yeah.
For instance, the results show that to reach a specific target loss value, such as 1.5, the optimized VoRA configuration required considerably fewer training steps compared to the baseline vanilla LoRA approach. Furthermore, this gap in efficiency appears to widen as they aim for even lower loss values.
Interesting.
Suggesting that VoRA has the potential to achieve comparable or even superior results with substantially less training data or time.
Now, a natural question for anyone following this field is, how does VoRA actually stack up against other existing state-of-the-art methods for building multimodal LLMs? Table 3 in the paper provides a comparative overview.
As the authors themselves emphasize, their primary objective in this work wasn't necessarily to chase the absolute state-of-the-art performance on every single benchmark at this initial stage.
Right, focusing on the architecture itself.
Instead, Their focus was on rigorously validating the effectiveness and the potential of the proposed VoRA architecture as a strong and efficient baseline model. To this end, they deliberately limited the amount of fine-tuning data used to the publicly available LLVA 665K dataset, explicitly refraining from utilizing the massive, often proprietary in-domain datasets that some other encoder-free methods rely upon.
And under those quite strict and controlled LVA 1.5 evaluation protocols, VoRA achieved performance that is indeed comparable to both the officially reported and their own reproduced ALVO 1.5 baseline results across the majority of the evaluated benchmark datasets.
That's right. It's a very promising result, especially considering the more constrained fine-tuning regime they adhered to. However, they do openly acknowledge that VoRA exhibited a degree of underperformance on the MME perception benchmark.
Ah, okay. Where did it struggle?
Table 4 provides a more granular breakdown of these results, indicating weaker performance on specific tasks that necessitate a significant amount of real-world knowledge, such as accurately identifying details in movies, recognizing famous celebrities, identifying landmarks, and classifying artworks.
And they attribute this observed underperformance primarily to the inherent limitations in the world knowledge present within their chosen pre-training datasets, rather than a fundamental architectural flaw in the VoRA design itself.
Precisely. Their analysis suggests that this is more of a data-related limitation that could potentially be addressed with the incorporation of more diverse and knowledge-rich pre-training data in future iterations.
Makes sense. You can't know what you haven't seen. So looking ahead, what are the key limitations of the VoRA approach as it currently stands, according to the authors in Section 6 of their paper?
The most significant limitation they highlight is the inherent reliance on a substantial amount of additional pre-training data to effectively compensate for the absence of a dedicated pre-trained external vision model.
Right, it has to learn vision from scratch, essentially.
In essence, yes. The LLM within the VoRA framework has to learn to extract meaningful visual features, largely from the ground up, guided by the distillation. While they hypothesize that scaling up the VoRA model and training it on even larger datasets could potentially allow it to surpass the performance of traditional encoder-based MLLMs in the long run.
By avoiding potential bottlenecks in the VIT.
Exactly. By potentially avoiding information bottlenecks that might occur in a separate pre-trained VIT, they currently lack the computational resources to empirically demonstrate this at a very large scale.
A common issue in academic research. And they also point out the current absence of any explicit vision token compression techniques in their current implementation, unlike some encoder-based methods that employ mechanisms to reduce the number of visual tokens passed to the LLM for processing.
That's correct. They intentionally maintain the original LLVA 1.5 configurations to ensure a fair and direct comparison, but they do recognize that the lack of vision token compression could be a potential area for future optimization.
Like using bigger patches or pruning tokens.
Exactly. Exploring techniques such as utilizing larger initial patch sizes for the images or implementing some form of visual token pruning could potentially improve efficiency and reduce computational costs further down the line. And as we discussed earlier, the observed underperformance on tasks requiring extensive world knowledge is another current limitation, which they strongly believe can be effectively addressed through the strategic curation and incorporation of more comprehensive and targeted training data.
Okay, so as we begin to wrap up this insightful deep dive, what are the key overarching takeaways from our exploration of the Vision as LoRA paper?
The core contributions of the VoRA paradigm are really threefold. First and foremost, the Vision as LoRA concept itself, which provides an elegant and efficient way to integrate visual understanding directly into a large language model by leveraging mergeable low-rank adaptation layers.
The core idea.
Second, their clever blockwise distillation strategy, which proves to be highly effective in transferring rich visual knowledge from a pre-trained vision transformer, thereby accelerating training and potentially reducing the overall data requirements.
Speeding things up.
And third, the strategic use of bi-directional attention masks specifically for processing the visual input, which demonstrably enables a better capture of the crucial global context within the images.
Better visual understanding.
Taken together, these make VoRA a really compelling approach.
So in essence, VoRA presents a genuinely interesting and remarkably efficient alternative approach to building multimodal large language models, but essentially internalizing the visual processing capabilities directly within the LLM architecture, effectively doing away with the need for a separate computationally intensive vision model during the inference phase.
Exactly. This internalization leads to a more unified and streamlined architecture characterized by reduced memory overhead and lower computational costs at inference time, all while retaining the crucial ability to process images at their native original resolutions.
Big advantage there.
Without being constrained by the fixed input sizes often imposed by external vision encoders.
And the authors also briefly touch upon the very promising potential for extending the core principles of VoRA to other modalities beyond just vision, such as audio processing or the analysis of point cloud data.
Yeah, that's exciting.
This could really pave the way for some incredibly exciting future research directions in the quest to build truly omnimodal AI models capable of understanding and interacting with the world through a much wider range of sensory inputs.
Absolutely. The inherent modality agnostic nature of applying LoRA based on leveraging the knowledge encoded in pre-trained expert models for different data types strongly suggests a very promising and potentially unifying path forward towards the development of more general-purpose intelligent systems.
The holy grail.
That can seamlessly understand and reason across diverse types of information.
So, for you, our technically astute listener who's always on the lookout for the next groundbreaking idea, I leave you with this thought. What are the broader implications of such efficient and unified multimodal architectures for the future trajectory of artificial intelligence? Could this type of approach be a crucial step towards realizing truly general-purpose intelligent systems without the inherent complexities and computational overhead associated with traditional modular designs?
I forgot.
And perhaps most importantly, what novel research directions does this innovative encoder-free paradigm inspire for you in your own ongoing work? It's definitely a fascinating area, ripe with potential. Thanks for joining us for this deep dive into VoRA.